So right, let me do this question. This is, as it says, it's a guided tutorial in derivation of intensity pattern for Young's double-slit interference, which is why I haven't done so far. But this is literally the last remaining question in this problem set. So for the sake of completeness, let me complete it. Let me demonstrate what you would go through as you go through this guided tutorial. But I strongly encourage you to try working through this on your own, because that's really the purpose of tutorial, that you are learning as you work through. It's a very long question. There's a lot of information that the question gives and asks. So I recommend that you go through it. And let me see. Do I want to read it out loud? Let me read it out loud. I know you know how to read. It's not like I don't think you know how to read the English sentences, but let me read it out loud so that I'm not rushing through this tutorial. So I already read the first sentence. Let me read the second sentence, and I'll just read it through until there's a question for me to answer. Standard treatments in lower division textbooks are done using real-valued trigonometric functions. In this tutorial, we'll make use of complex representation of oscillatory functions covered in lecture and other exercises. Feynman lecture section 29.5 is another available resource. It's the only written available resource. The figure shows the arrangement for consideration of light waves arriving at the same point P on a screen very far away. Like this. So in this diagram, it doesn't show how far away it is really. So this diagram, part B, is showing that we treat these rays as basically being parallel because the screen is so far away. And for this is accessibility feature, which if you can see the figure, then you don't need a figure description. If you can't see the figure, then you do need a figure description. For a screen very far away, you consider the two light paths from S1, slit 1, and S2, slit 2, to be nearly parallel as shown in part B of the figure. Let E1, as a function of time, describe the electric field at point P due to the light wave passing through slit S1, and let E2, as a function of time, describe the electric field at point P due to the light wave passing through slit S2. Okay, with an appropriate choice of relative phase and electric field amplitude E0, we can express the two electric fields in the form E1 of as a function of time being E0 times the complex exponential e to the I omega t, and E2 of t equal to E0 times e to the I parenthesis omega t plus phi. Okay. Find an expression for phi in terms of slit spacing d, wavelength lambda, and angular position theta. So all this information that's here, I think it's just a prelude. You don't need to answer this part. To answer this part, you need this figure. So you look at this part B figure. This is delta L, the difference in path length. So the image that's given to you already gives you the path length difference. And considering this right triangle here, you can see that, oh, the L must be equal to the hypotenuse, d, times sine theta. And for part A, that's going to relate to the phase difference, or the phase vector phi. I guess the reason they gave you all this is to, in a roundabout way, define the symbol phi. This is what we call phase factor. It's the phase difference between the two sources. E1 doesn't have it. You add it to E2. That's the difference. So anytime you have some kind of length that you want to convert into phase angle in radians, is that phase is that distance expressed as a fraction of wavelength. So you divide by lambda wavelength. This will give you fractions of cycle, which is not what you want. You want the angle in unit of radians, 2 pi. This is the factor that converts from number of cycles to radians. So that should be the expression. Let's see. So I can use lambda. I can use, well, I probably can use 2 pi. They are all constants. So I need delta L expressed in terms of d and theta. So just rearranging a little bit, 2 pi over lambda times delta L, or d sine theta. That should be it. Let's make sure I didn't make any. Oops, 2 pi over lambda. And if you don't know what to type in, you can actually kind of click stuff here. So here I need a function. Oh wait, no, I need a variable d times a function of trig function of sine variable theta. So you could just click through. I prefer typing; it's a little faster for me. Let me submit this. Make sure I'm on the right track. When you submit one part, you're not submitting anything for the other parts. Very good. Okay. Let's keep going. Format hint. Yeah. Using the superposition principle, find the total electric field at point P as a function of time, E total as a function of time. Use the complex exponential representation to fill in the blank below. As you look at this, look at the blank. If you remember superposition principle, that's a very grandiose name for a very simple mathematical operation. Simple addition. Applies whenever you have linear relationship. So that should be just the sum of these. So it's just going to be some of the exponential things. I omega times omega times t plus exponential of I times omega times t plus phi. One more parenthesis? No. It'll probably accept this as correct, even though I might have issued the inner times that being ambiguous. But I think the system will accept that as correct. So if you've been following lectures, you understand superposition principle. This is asking for a very simple thing. What is the expression for sum of these two functions? Keep going. An important note about complex representation. You can do most operations you do with real valued trigonometric functions with the complex representation, which is good. Otherwise, why would you use complex representation? For example, given functions f and g of time, and the complex version of f and g as a function of time, following operations are valid. You can do addition, you can do subtraction, you can do multiplication by a real number, you can do differentiation, you can do integration. And what it means by valid is you can do that operation just with the real valued functions, or you can do it with a complex version of the function and just take the real part at the end. You will get exact equality. I think the first three might not be as surprising, but differentiation and integration, it might be surprising to some people. This is just mathematical fact. Try the last two in particular with examples. F of t is a times cosine of omega t, and f, the complex version of t, is equal to a times e to the I omega t. And I think the next part will have you actually do this, so I'm not going to actually do it right now. Read on. You have to be careful, however, with any operations involving multiplication to be contrasted with this, or division, which is a form of multiplication. For example, multiplication by a complex number. It's not a lot. So here, I guess you're actually technically multiplying two functions, but this product of two real functions is not going to be equal to a real part of product of these two complex functions. Just can't rely on that. Try it out with the example f of t is cosine omega t and g of t is cosine of omega t, with the corresponding, the complex version of f and g of t being e to the I omega t. I guess we'll keep reading. Yeah, so I think it's you're meant to try it out, kind of play with it. In the interest of time, I'm just gonna move on. But I encourage you to spend a little more time. I don't know, put that into calculator, make sure you have some intuitive feel for it. As a special case, if you are interested in time averaged value of f of t squared, which is f of t squared is equal to f of t multiplied to itself, you can calculate this using the complex representation, using this special formula for a generic oscillatory function f of t, amplitude times cosine of omega t plus some phase factor is going to be equal to the time average. And I think I did this in lecture, how to simplify cosine squared of omega t, use power reducing formula, and when you do that, you get an expression that's going to be I think a squared divided by 2. And you can get that exact same expression using this version on the right-hand side. It's something you can prove for oscillatory functions that goes as e to the I omega t. The left-hand side represents a time average. For convenience, let t represent one period of the cycle. And on the right-hand side, the f conjugate of t is the complex conjugate of f, the complex version of t. This special case will be proved at the end of this problem for your reference. Oh, well, did I actually do that? We'll see. Calculate and simplify all this. Okay, I guess I can do that. Let me just write down the E total for kind of reference to myself, so I don't miss anything, I don't forget anything. So for part B, we are going to have E complex total as a function of time is equal to E naught times E to the I omega t plus E to the I omega t plus phi. Okay, so with that E total, it's asking calculate and simplify this. Okay, I can do that. Let me start by writing down the E complex conjugate. If you have forgotten the complex conjugate operation, all it does is basically wherever you see imaginary numbers, turn them into minus I. If you see any complex number, you should also turn them into complex conjugate. Here, I've written down my expression so that all these parameters they are designed to be real. So I'm not going to say any of those parameters are complex. So the version where all these i's might have been turned into negative sign, it's going to be E naught times E to the minus I omega t plus E to the minus I parenthesis omega t plus phi. Okay, let's write that. Oh wait, I can't write it down. It's not asking for that, it's actually asking for product of those two complex numbers, then divide by 2. Alright, let's do that. I think I can do it. E total times E complex conjugate total is equal to, let me do the multiplication in my head, except for, I'm going to write down 4 terms, and as I write them down, I'll do the algebra in my head. So we start out with the E naught squared. It's coming from multiplying these two, and we are going to have 4 terms. So ei omega t multiplied to e to the minus I omega t, that's first term. So that's going to be just equal to 1, because they will cancel each other out. The exponential algebra, or you can express this as 1 over e to the I omega t. Okay, let's do this multiplication, e to the I omega t times e to the minus I omega t minus I phi. Then, so let me just write it out for my own clarity. So on the exponent, the products, they become sums. So it's going to be e to the I omega t minus omega t minus v. I've left I filtered out. So what's going to look like is you'll have these two terms canceling, and you'll have e to the minus I phi. Okay, that seems not wrong. Complicated, but not wrong. Let's keep moving. So that's that product. We now need the product with the second term going this way. It's going to be plus, so e to the I omega t plus phi minus I omega t. So it'll be e to the, this time I'll just write the final expression. It should be e to the I phi. Okay, the final connection, e to the this, multiply by e to the that. And kind of same with the first term, when you do that, you end up giving you plus 1. Those are the 4 terms. And I'll bet you can just leave it that way. Do I have to? Oh, wait. It says this. So make sure you simplify your expression enough so that it is evident that your result is a real valued function. I think what that means is if I type in squared times 1 plus e to the minus I times phi plus e to the I times phi, oops, times phi plus 1. It'll probably say that's wrong, I think. Syntax error. It says in terms of phi. Let's see. It should still say it's an error because it's not. This is not the intended answer. So I'm not sure about that error message. What I will tell you is that you really should combine these two. So this is fine. That's real. One that's fine. It's real. One that's fine. That's real. Your issue really comes from this part here. So what you have is e to the I minus I phi plus e to the I phi. And without going into a whole long series of explanations, I recognize this as 2 times the cosine of phi. And part of the recognition is based on the fact that I have this memorized. So if you want to represent the trigonometric function cosine of theta in terms of exponential functions, then that's going to be e to the I theta plus e to the minus I theta divided by 2, I think. And just double checking, when theta is equal to 0, you do get 1. Was there an I somewhere? No, I think that's fine, yeah. And for sine of theta, you have e to the I theta minus e to the minus I theta over 2i. And if you want to prove any of this, you would just use Euler's formula, which says e to the I theta is equal to cosine of theta plus I sine theta. I think once someone gives you these two expressions, then it's relatively easy work showing that whether this is substituted in, this particular combination is indeed the cosine of theta, and the bottom half of the configuration is the sine theta. So with all that, what I'm saying is that, I probably should rewrite this. And looking at, okay, it kind of looks like this, especially if I move the 2 over, then it looks identical. So this should be 2 times the cosine of phi. So let me make the change, and let's see if it this time accepts what I'm doing. So 2 times cosine of phi. Okay, syntax error is gone for some reason, and let's hope it's actually what I'm looking for. What did I miss? Real valued function. Divide by 2. I forgot to divide by 2. So that'll get rid of this 2. And I had a 1 plus 1, 2. So dividing by 2 will get rid of 1. So, all right, now you should be right. This is why you have infinite attempts, so that if you miss something trivial, that doesn't trip you up, or that doesn't cause you to lose points. Okay. Oh, and I guess I had all this hint. Yeah, I swear I'm just looking at it. The time average intensity, I average of light, proportional to is proportional to the square of the amplitude of the optical electric field. That's what we are using here. I average is proportional to E naught squared. To avoid having to work out the constant coefficient, we can express intensity of a double-slit interference pattern in terms of the intensity at the central maximum, I naught, at I equals theta 0. Write down below the average intensity of the double-slit interference for a double-slit interference pattern in terms of I naught, phi, and possibly omega and t. What? I guess all this is saying is it's defining I naught. So they want us to use I naught instead of the electric field. Okay, so I do have a question. So in terms of, I don't think I naught is some sort of a hypothetical intensity where the uh, the number of slits is 1. So I think so we already worked out E squared. I think that's a good starting place. So E naught squared is equal to the N0 squared average is equal to what we have here, because that's really the statement being made in part B about the theorem. So as a special case, if you're interested in the time average the value while you are dealing with the oscillating quantity of electric field, it's saying you can calculate this, meaning the time average value, using the complex exponential representation, the right hand side, without actually doing any integral. So here what I do say is that E0 average should be I'm just copying this formula over, then it again should be 1/2 E0 complex conjugate times the E0 itself. That feels like something I've already done up here. So let me just plug it in. So this is equal to E0 squared, that's that one, divide by 2, that's the division by 2 there, and then the rest of the factors. So 2 plus 2 cosine phi. 2 plus 2 cosine phi. Okay. What am I thinking about? Yeah, I average. So what you need to say is that so if we say the E0 squared is proportional to the intensity of a single slit, then I don't think that's what we are doing though. Well, let me finish writing this. So if we say this, then we also can say the so this isn't E0, this is like E total. E total. Then what we can say is that E total squared is also proportional to the I average, and I'm saying all the average has been done at center. Okay, so I already have all this expression. So just staring at this for a bit, staring at this, what I have to say, okay, my intensity average total is equal to, now let me read it carefully. We can express intensity of double-slit. It's better in terms of, okay, so it feels like it's already setting what I0 is. It's the intensity at theta equals 0, the central maximum. Then, so I average should be squared, absorbing into 1 plus 1 cosine phi. And by this connection we are making, we are saying, are we saying that E0 squared is I0? Let's see, I0 times 1 plus cosine phi. Okay, I don't think that's what we possibly mean, because when I plug in phi equals 0, or if I plug in phi equals 0, which is the result of setting theta equal to 0. Remember, we have this relationship between phi and theta. So we will probably be using it at some point. So when theta is equal to 0, that makes your phi equal to 0, because there's no nothing else in this expression where with the sine theta being equal to 0, something that can make phi something other than 0. So with all that, this is what the expression should be. So I want to make it so that when phi is equal to 0, because theta is equal to 0, this average intensity is just I0. And right now we don't have that. When we plug in phi equals 0, this is 2, so I get 2 I0, which I don't think is how the question was setting this stuff up. So I'll say my final expression for I average is I0 divided by 2, 1 plus cosine phi. If considered right. It's possible I either made a mistake in the past or am making a mistake right now. 1 plus cosine of phi. Yeah, we can use it in terms of phi. Yeah, so that would be right. See? I think that was graded as right. Good. We introduced the phi as a function of theta, yeah, to help identify simplifying writing down expression for the I-average theta, but for comparison with the intensity measurements that may be made in a real experiment, we need an observation of for intensity as a function of physical angle, yeah. Using your results in A and D, write down below an expression for I-average in terms of, so I guess I was already doing it partly. So I think all I need to do is really plug in this expression for phi here. I think that's all I need. To the expression that we had before, I don't really need to rewrite it this way. So let's just do it this way here. So I'm gonna imagine plugging this phi into here. It really doesn't simplify. So all you can do is, all right, my intensity average now is a function of theta, not phi, is equal to I naught over 2 times 1 plus cosine of that whole expression. You will have nested trig functions. I don't think there's really a way to avoid it. So just doing it. I think that's probably the correct expression. Let me give it a try. Make sure I didn't make a mistake in my sleepy state. So 2 times pi divided by lambda times d times sine theta. All right. Let's hope that's right. Oh, okay. Yeah, that's right. And I guess that's it. Yeah, so that's the expression for your I average. And this actually, that is your intensity of double-slit interference pattern as a function of theta. So this is valid for any angle theta, going from 0 to 90 degree. We didn't use a small angle approximation. And if you use a small angle approximation, then you can say sine theta, or that's approximately theta. So it becomes 1 plus cosine of, that just linear factoring theta. So good. Oh, I guess the proof of the special case is not part of the tutorial. That's why there was all this material remaining, but we are done. Yeah, so that's what it says for the proof of the... Yeah. So as a special case, it says special case will be proved at the end of the problem for your reference. So if you are interested, you can read through this one-page proof also. So it's a proof that really only applies when you have an oscillatory function of known omega as a function of time. That kind of allows you to write the complex version this way, and that leads to, in the end, the cancellation of some of the factors. So you can follow the proof if you want, but since that's not part of the problem, let me not do it right now. So this is a tutorial. Yeah, it took long. That's another one of the reasons why I didn't do this question before, because tutorial questions are long. The intent is that you are learning as you work through the problem. So that's what I recommend that you do. If you're wondering about answers for some of these, then all right, you got my answers. And I should have coded them in such a way that a lot of these are robust to many common kind of different ways people might have written down these things. Like if you wrote it this way, it should have still graded it as correct. It shouldn't have done anything differently. And yeah. But I'm pretty sure you can't do the weird thing like I think I already did this, right? So you can't write it this way. So this is the complex version of the cosine of phi. So I'm not denying that what I'm writing here is mathematically equivalent to what you have before, but the instruction set write it clearly. That's why it says make sure you simplify expressions so it's evident that your result is a real valued function. Because the algebraic evaluation function that's available with the MyOpenMath, it's not all that sophisticated. It cannot tell you all the different ways of getting what is basically equivalent expressions. You can't do that, so don't try to make it do that. Don't torture MyOpenMath. Let me just try one more thing to know that, yeah, it still won't work. Good. Any questions? Let me know, please, either here or by message later for those of you watching the recording.